Hello friends, in this session we are going to see vector calculus. Here we are discussing vector calculus. Okay, so for the coordinate system that we know is the Cartesian coordinate system. Cartesian coordinate system where the bases are x cap, y cap and z cap. That means any vector is a combination of x cap, y cap and z cap, and the conditions are x cap dot x cap equal to y cap dot y cap equal to z cap dot z cap equal to 1. Now similarly we can write x cap dot y cap equal to y cap dot z cap equal to z cap dot x cap equal to 0. This is just like the normalization for wave function, and this is similar to orthogonality condition of wave function. Now any vector A, as mentioned earlier, can be put in terms of x cap, y cap and z cap. So we can write A x into x cap, A y cap, A z cap. These are the ax, ay and az are x, y and z coordinates, and the range of x is from minus infinity to plus infinity. Similarly for y and z, all are from minus infinity to plus infinity. Now I am introducing a quantity called metric element. So the metric element for the Cartesian coordinate system is 1 1 1. This each value corresponds to x, y and z coordinates, which means if I want to write some change dr, small length element, then dx into x cap, that means the matrix element 1 into dx into x cap plus another metric element 1 into dy y cap plus the third metric element corresponding to z into dz z cap. Now the each length element are dx, dy and dz. So this will be the corresponding length. The area element, this is the length element, so this what is we have given. The area element is given by, that means the small area ds vector is equal to first one dx dy. Dx dy will be in the direction of z cap, dy dz will be in the direction of x cap, and dz dx will be in the direction of y cap. So these are small area element in the Cartesian coordinate system, and this direction z cap, x cap and y cap will be always outward, and it's always as usual, obviously it will be normal. Now we have the volume element, which is given by dx dy dz, which is equal to dv, or sometimes we may not denote it with d tau. Now for any vectors a, b and c, the volume is given by a dot b cross c. So kindly remember this. The next coordinate system is cylindrical coordinate system. For the cylindrical coordinate system, the bases are rho, phi and z, and as we have seen in the case of Cartesian coordinate system, rho cap dot rho cap equal to rho cap dot phi cap dot phi cap equal to z cap dot z cap equal to 1, and similarly rho cap dot phi cap equal to phi cap dot z cap equal to z cap dot rho cap equal to 0. Now any vector A in a cylindrical coordinate system can be represented by a rho, rho cap, plus a phi, phi cap, plus a z, z cap. So a rho, a phi and a z are the elements for the coefficient of rho, phi and z, and now we need to find out the limits of rho. Rho is from 0 to infinity, the range of rho is from 0 to infinity. The phi ranges from 0 to 2 pi, and z ranges from minus infinity to plus infinity. Okay, so the metric element we am denoting it by 1 rho 1, and it is denoted, the metric element is h1, h2, h3, and for the cylindrical coordinate system we say it is equal to 1 rho and 1, that is the metric element corresponding to rho is 1, metric element corresponding to phi is rho, and metric element corresponding to z is 1. That means any element, length element dr is written as d rho into rho cap plus that means here you need to write 1, that is the metric element 1, d rho into rho cap. Now you have the metric element rho d phi cap plus 1, that is 1 into dz z cap. So here there is we have added the metric element rho, since rho is the metric element corresponding to phi. Okay, so we can write it as d rho cap plus rho d phi phi cap plus dz z cap. Now if you want to convert it this cylindrical coordinate system to Cartesian coordinate system, we have to write this x is equal to rho cos phi and y is equal to rho sin phi, and the value of z is equal to z. The length element in the cylindrical coordinate system along each direction is given by d rho, rho d phi and dz. So these are the length element. Now the area element is just take the product of 2, so it is d rho into rho d phi, so it is rho d rho d phi. The second one is just multiply with d rho with dz, so it is, and you have to also write down the vector, that is z cap. Now I am multiplying this with this, so it becomes let us write down d rho into dz, which will be, if I write like this, d rho dz, it will be in the direction of phi cap, but since I have taken it in the reverse order, it should be always going in the cyclic order, 1 2 and back. Okay, so if I have changed the order, I have to put a minus sign. Okay, now, or what you have to write, rho d phi dz, rho so let us write here rho d phi dz in the direction of rho cap, and one more thing you can write, dz, also that is here we have already written this, you can change it in the form of dz d rho in the direction of phi cap if you go cyclic. Now the volume element dv, volume element dv is equal to, just take the product of all the length element, that is rho d phi dz, or you can also write it as d tau. So this is about cylindrical coordinate system. Third coordinate system that we are dealing with, that is spherical polar coordinates. Okay. So here we have the basis as r, theta and phi. Now as we have proceeded with the other two coordinate system, we will do r cap equal to theta cap dot theta cap equal to phi cap dot phi cap equal to 1, and r cap dot theta cap equal to theta cap dot phi cap equal to phi cap dot r cap equal to 0. So this is the normalizing conditions like we have in the quantum mechanics wave function, and this is the orthogonal condition. Now any vector in spherical polar coordinates A can be written as AR into r cap plus A theta into theta cap plus A phi into phi cap, where AR, A theta and A phi are the elements in the spherical polar coordinates corresponding to r cap, theta cap and phi cap respectively. Now coming to the range of r varies from 0 to infinity. Please kindly note it is not from minus infinity to plus infinity, it is from 0 to infinity, and theta is moving from 0 to pi. Again please note it is from 0 to pi and not the entire 360, it is 0 to pi, and the phi varying from 0 to 2 pi. Okay. Now let us also write down the metric element in spherical polar coordinates, that are 1 r and r sine theta. So this is the metric element. So any vector dr can be written as that means dr is equal to any length element. Okay. So dr, that means the metric element corresponding to r, that is 1 into that dr, small change in dr, into r cap, the unit vector, plus the metric element corresponding to the theta. This is r, this is for r, this is for theta, and this is for phi. So metric element corresponding to theta is r, and it is d theta, r d theta, in the direction of theta, that is theta cap, plus you have to write down the metric element corresponding to phi, which is r sine theta into d phi into phi cap. So this is the entire vector, or the length, small change in length is given by dr r cap plus r d theta theta cap plus r sine theta d phi phi cap. So this is corresponding to the length on radius. This is theta, r d theta, and r sine theta d phi, that is corresponding to angle phi. Now the length element we have, once again you can write that length elements. What are the length element corresponding to each of the coordinates, that is dr and r d theta and r sine theta d phi. Now we have the area element. So area element is nothing but 1 2 into the direction of third. So dr into r d theta. So let me write r d theta, just the multiplication, and in the direction of the third, that means in the direction of phi, because area element is a vector. Okay, this is one. Now the next one is 2 into 3 in the direction of the other. So r d theta, so we can write r d theta times r sine theta d phi. So r square sine theta into d theta d phi, and it should be in the direction of the r. Okay, so plus, now you have to do this 1 2 in the direction of 3. So r dr sine theta, r dr is there. Okay, so r sine theta dr d phi, and it should be in the direction of theta. So this is theta cap. So this is phi cap direction unit area vector. This is in the direction of r cap, and this is in the direction of theta cap. Now coming to the volume element. Product of all the three, that is r. So r square dr sine theta d theta d phi. So okay, fine. So r square sine theta d theta, okay, it's dr d theta d phi. Okay, so or you can write it as r square dr sine theta d theta d phi. This is because when you integrate, you can, this is the first term, this is the second, and this is third. Okay, this is volume element dv or d tau. Okay, yeah. So let us also write down what are, according to the coordinates x, Cartesian coordinate, how you can write the x in terms of spherical polar coordinates. Okay, it is r sine theta cos phi, y is equal to r sine theta sine phi, and z equal to r cos theta. Okay, so kindly remember the points noted. Now here we are going to see for a general coordinate system. Kindly note, this is not the generalized coordinate system, it's a general coordinate system, just like Cartesian, spherical, and cylindrical coordinate system. Okay, so general coordinate system. Let us give some name to the basis, that is, let it be q1, q2, and q3. This is for 3 dimension, any 3-dimensional general coordinate system. So basis I have to write it as q1 cap, q2 cap, and q3 cap, and corresponding the coordinates are q1, q2, q3, just like x, y, and z. Now the metric element I am writing as metric element, that's equal to h1, h2, h3. So this is for any generalized coordinate system for 3D. Metric element h1, h2, and h3. Now these are the basis, and this is the corresponding coordinates. Okay, and this is the metric element. All are in order, so we need not mention that once again. So any vector dr can be written as h1, that is the metric element, h1, q1, that is the basis or the unit vector, and this is the coordinate. So I will take h1 dq1 into q1 cap, okay, plus h2 dq2 into q2 cap, plus h3, that is the third metric element, dq3 into q3 cap. Okay, so that's it. So if you want to write down the area vector, so it will be product of these two. First two, let us take h1 h2 dq1 dq2 into q1 q2, and it should be q3 cap. Okay, in the direction of the other, product of 2 in the direction of third, plus. Okay, so now this is, sorry, not plus, this is another area vector, h2 h3 dq2 dq3 q2 q3, and this is q1 cap, not q4, it is q2 q3, so it will be in the direction of the cyclic one. So what is cyclic? It should go from q1 q2 q3, it goes from q1 q2 in the direction of third, q2 q3 in the direction of q1, and q1 q3 q1 in the direction of q2. So the next area element or area this one will be equal to h3 h1 dq3 dq1 in the direction of q2. Okay. So volume element, that is dv, is equal to h1 h2 h3 dq1 dq2 dq3, and in the direction, there is no direction, it is a scalar. So here we are going to see del operator. Del operator. So this is the symbol for del. Now there are different uses for this del. Usually it is gradient, divergence, curl. This is what you are going to find. For now, let us see one by one the applications of this del, that is from scalar to vector. We are changing a scalar to vector. Okay, we use this something called gradient of a scalar. So you can remember it, gradient of a scalar. So how we write, if we have this scalar phi, the vector is del phi, that is the gradient of this scalar. This particular quantity is a vector. Okay. Now very good example that we can give is electric field E is equal to minus del V, where V is the potential, scalar potential. Okay, this V is a scalar potential. And here this is the electric field. Now coming to the second application, that is to convert vector to scalar. Now here we say it is divergent or divergence. Okay. Now divergence of a vector, we are converting to a vector to scalar. So we say divergence of a vector. So del dot A. So del dot A. A is a vector. We are getting a scalar quantity. Now del dot E. This is one good example where you can write del dot E, that is the Coulomb's law, Gauss law in divergent form. So it's rho by epsilon naught. Or in magnetostatics, you can write del dot B equal to 0. Or again del dot J, the current vector, current density del dot J is equal to minus dou rho by dou T. Okay, so that's some applications where you convert a vector to scalar. No, actually this is not converting, this is giving a scalar form. Okay, different form to that. Now the third one is from vector to vector. Now this is called curl. When you do that, this curl. So you remember it in this way: gradient, divergence, and the curl. So del cross A. Del cross A is a vector, and A is also a vector. Now a good example is del cross E minus dou B by dou T. That's a second Maxwell's equation. Again you have the fourth Maxwell's equation, del cross B equal to mu naught J plus 1 by C square dou E by dou T. Again we have del cross A, where A is a vector potential, del cross A equal to B. This is magnetic field. Suppose if there is any vector, A, then whose curl is 0, so that means del cross A, if you are getting, if this is equal to 0, then you can represent A, or you can say A is irrotational. Okay. Here we are going to look into the del operator in generalized coordinate system. General coordinate system, operator in general coordinate system. Okay, so in general we can write del, and for let us write down what we require for a general coordinate system, that is q1, q2, q3. These are the coordinates, and corresponding bases are q1 cap, q2 cap, q3 cap, and their corresponding metric element are h1, h2, h3. So these are the things that we need to construct the del operator. So that's equal to q1 cap by h1 dou by dou q1 plus q1 cap by q2 cap by h2 dou by dou q2 plus q3 cap by h3 dou by dou q3. So this is del operator in general coordinate system, and for example you can write from this general coordinate system for let us find out for spherical polar coordinates. Okay, for spherical polar coordinates, how can you write this? For spherical polar coordinates, what are the coordinates? These are r, theta and phi, corresponding the unit vectors are r cap, theta cap and phi cap, and corresponding metric element h1, that is we know it is 1, this is r sine theta. Okay, so how can we write this del operator? So that is q1 cap, that is q1 cap is nothing but the first one, that is r cap divided by h1. H1 is 1 dou by dou r, plus this is q2 cap. Q2 cap is what is q2 cap, that is theta cap, by h2. What is h2? This is r dou by dou r, plus what is q3 cap? Q3 cap is phi cap divided by r sine theta dou by dou phi. So this is del operator in spherical polar coordinates. Okay, now let us write down the divergence. Here you can also write the del operator in Cartesian coordinate system as well as cylindrical coordinate system, just for practice. So divergence we can write of a vector. Let us write down the vector first, that is A is equal to A1 Q1 cap plus A2 Q2 cap plus A3 Q3 cap. Del cross, divergence, it is del dot A, this is given by 1 divided by h1 h2 h3 dou by dou q1 of a1, and the other two are h2 and h3. Okay, h2 h3. So the first one is belonging to the vector, h2 and h3 are the metric element. Okay, so it goes like this: dou by dou q2 a2 h3 h1, not h4, plus dou by dou q3 of a3 h1 h2. Okay, so that's it. You can also find out for spherical, cylindrical and Cartesian coordinate system the divergence of this vector. So curl of the vector, this is what we are going to see next. So curl of vector in general coordinates. So del cross A, and what is A? A is A1 Q1 cap plus A2 Q2 cap plus A3 Q3 cap. So this is curl of the vector, and we have to find out del cross A. The metric element are h1 h2 h3, and the bases are q1 cap, q2 cap and q3 cap. So this is equal to 1 divided by h1 h2 h3, the product of all three, and now we are going to find out the cross product. This is h1 q1 cap, h2 Q2 cap, H3 Q3 cap. Just like we write x cap, y cap and z cap when we are making a cross product. So here we have dou by dou Q1, dou by dou Q2, dou by dou Q3 as the third element. This again, here you have H1 A1, H2 A2 and H3 A3. Now you make the cross product, and whatever you are getting, you have to divide it by the product of H1, H2, H3. This is what you are going to get. Now suppose for the three-dimensional coordinate system, that is Cartesian coordinate system x, y, z, we have the metric element 1, 1, 1, and the vector A is equal to ax into x cap plus ay y cap plus az z cap. Okay, and the corresponding vectors. Okay, now so let us write down in what will happen. So 1 by 1, so we need to find out only the cross product. H1 is 1, Q1 cap is x cap, Q2 cap is y cap, Q3 cap is z cap. H1, H2, H3 are 1, so it is dou by dou x, this is dou by dou y, dou by dou z, and this is ax, ay, az. Okay. Okay. Now let us also write for the cylindrical coordinate system. What are the coordinates? That is rho, phi, z, and the metric element 1, r, and 1, right? So let us just confirm it. So this is 1, row 1. Okay, yeah. Now the cross product, let us also write down A is equal to A rho into rho cap plus A phi into phi cap plus AZ into Z cap. That is vector A. Fine. Now 1 divided by H1, H2, H3, that is the product of this, so 1 by rho, and now we are doing the cross product. This is rho cap, this is phi cap, this is Z cap, and dou by dou rho, dou by dou r, that is phi, dou by dou z. Okay, this is a rho, that means the component corresponding to rho coordinate. Okay, then a phi, az. Okay, so this is the del cross A, that is the curl of the vector. This is how you find. Now similarly you can find out for spherical polar coordinates what is del cross A. Here we are going to discuss some applications of gradient. So now we are just finding out some scalar field. Okay, we have a scalar field which is given by phi let this be some f of x, the function x. Then del phi is nothing but it is a vector. It will be a vector which is normal to phi, normal to phi, or normal to the surface. Okay, so for example, if this is the function f of x given by phi is equal to f of x, then the del phi, the gradient of this phi will be, if you at this particular point it will be pointing normal to this surface. If you're finding at this particular point, it will be again normal to this surface. At this point it will be again normal. So this, whatever vector you are going to get, at each point it will be a vector which is normal to the phi. Okay, now what does this del phi, the magnitude of del phi, tell you? This tells you how rapidly function increases or decreases, how rapidly the function f of x or the phi just we have discussed increases or decreases, increases or decreases. Okay. And you can also mention this del phi by the magnitude of del phi. This will give you some unit vector n cap, and this is the direction in which the function increases or decreases rapidly. Now this is the unit vector where you can define, it is the defined as the direction in which the function f of x or the phi increases or decreases. So the vector n cap only gives the direction where the function decreases or increases, and this magnitude tells you how rapidly it increases. Whether the, for example, if you consider this as the hill, what is the steep of the hill? If it is very, what that means, you are actually finding out the slope. Okay, slope of a curve or a slope of the function, or for example, if you consider this as the hill, this is slope. Okay, the higher the magnitude means higher the slope. Okay. Now good example we can write as an example is electric field is equal to minus del V. Now E is, or what is the E? E is the electric field. Okay, electric field, and it is pointing in the direction, its direction is in such a way that direction is such that V is decreasing. It is in the direction where the potential is decreasing. Okay, now how can we justify that? We will just take an example of the same electric field of a point charge. Now let us this the point charge plus q. Okay, now as the distance increases, now I am moving from one point, this is the center O 0, and it is the x-axis, and it moves. Now it is decreasing, and q value is that is the charge. Now as you go from this 0 to x, the value of the potential. Now here you have potential is decreasing. Now from here to here, if you take for example, this is 10 volt and it decreases to here to 2 volt. So from when it moves from let's say for example x equal to a to x equal to b, the potential is decreasing. Now electric field direction is in this way, right? Electric field is in this way. So what does this E equal to minus del V says is that the direction will be in such that it is negative of del V. So it is pointing in that direction where the potential is decreasing. This is what is meant by E is equal to minus del V. So E is the direction. Now the magnitude, del V magnitude is nothing but the electric field, the value of electric field. The next kind of application is finding out the angle between two surfaces. Now find the angle between two surfaces. Now let's say for example there are two surfaces. Let us call it as phi 1 and phi 2. Then we can represent the n1 cap as equal to del phi 1 by the magnitude of del phi 1. So this gives you the vector in which will be perpendicular to the surface. Okay. Now similarly you can find out n2 cap, which will be the gradient of the phi 2 by the magnitude of del phi 2. Now this will give you the perpendicular direction to phi 2. So let us say if this is a surface phi 1 and this is another surface which is phi 2, then angle between these two surfaces will be nothing but if this is n1 cap and this will be n2 cap. Now if you could find the angle between n1 cap and n2 cap, you will arrive at the angle between phi 1 and phi 2, right? So we can write from this n1 cap dot n2 cap is equal to magnitude of n1 cap into magnitude of n2 cap times cos theta. But we already know that n1 and n2 are unit vectors because it is the vector divided by its magnitude. So you can write n1 dot n2 in this way. So cos theta is this one, so which will be equal to simply cos theta because the magnitude of n1 and magnitude of n2 are equal to 1. So theta will be equal to cos inverse of n1 cap dot n2 cap. So this value will be as nothing but the angle theta. Here we are going to see another application, that is the directional derivative. So here we have this is the curve that we have, let me call that as our phi. So what we are going to see is directional derivative. Now the idea is, we know that in if this is the del phi, now let me write, this is del phi, and this is the direction where the function phi increases or decreases rapidly. So this is del phi. We know that as, let me call this as some vector n. So n vector is the direction in which the phi varies rapidly or decreases or increases rapidly. Now I want to find a direction, or I wanted to find on any arbitrary direction A how the function or phi varies. So in this direction it is the maximum variation, maximum increase or decrease. Okay, so in this direction it is the maximum increase or decrease. Now I wanted to know in this direction how much increase or decrease happens in this direction. So this is some vector arbitrary direction A. So what we have to do is we have to project this vector A on del phi. So we can write n vector dot a cap gives you del phi, n is del phi dot a cap, sorry, vector A. Now since we need the direction, we have to divide the a vector by its magnitude, because we don't want the magnitude but we want only the direction. So this we will write it as a cap. So our formula is n vector dot a cap is equal to del phi dot a cap. Or you can write, since a cap is a unit, the magnitude is a cap, so del phi cos theta. Okay, so the rate of change of the function in an arbitrary direction A. So this gives you the rate of change of phi in the arbitrary direction A, or a cap. Okay, now some as a note you can take this. What is del phi? Del phi is the rate of change of phi in, or you can write the magnitude del phi. Magnitude of del phi is rate of change of function in del phi direction, right? So del phi direction is in this way. So in this way the magnitude is del phi magnitude, and n cap direction. Okay, so del phi magnitude will be maximum in this direction, and it will be the function of the cos of this angle theta in any other direction. Okay, the next application is equation of tangent plane to the surface. Equation of tangent plane to the surface. So surface is nothing but our phi. We have to find out a tangent plane to this surface. So this black uh, surface is our phi, and this one in orange is the plane which is placed over this surface phi such that it is tangent. Okay, so here we can take 2 points. That means here you have a point which touching the surface, that let me write it as the x naught, y naught and z naught. So x naught, y naught, z naught. So this is the point, and if I am drawing a perpendicular, this will be del phi, and this point somewhere on this plane, we can write it as x, y and z. Okay. Now from some center O, let us have these 2 points. That is, one is r naught and the other vector is r. Okay, now del phi dot r minus r naught will be equal to 0. Now what is this r minus r naught? These two are vectors, r and r naught. Now this particular vector is nothing but r minus r naught, r minus r naught. Now if you take this as a triangle from O, this is A and this is B, so OAB, if you consider as the triangle, then OA equal to R, OB equal, sorry, this is R naught, and OB equal to R. In this triangle you can see, when you apply triangle of vector addition, you can know that r minus r naught will be equal to AB, so which is a vector, and del phi dot r minus r naught, because we know that del phi is normal to the plane, sorry, normal to the vector phi, while r minus r naught is parallel to the plane, and as well as perpendicular to this what is it, phi, parallel to the plane, which means when you make the dot product, del phi dot r minus r naught will be equal to 0, because this angle will be always 90 degree. Then you can get what so called our equation of a tangent plane to the surface, that is nothing but del phi dot let us write r minus r naught itself, or you can write it in terms of del phi dot AB, vector AB, the del operator we have seen, and it is written as in this form, and we have another operator which is called Laplacian operator. Laplacian operator, which is called del squared. Now del square is nothing but del dot del. Now in general coordinate system, coordinate system. We can write the del square as, now let us write down what are the basis and the coordinates of general coordinate system. Let us write down as q1, q2 and q3. These are the basis, and the metric elements are h1, h2, h3, and the bases are q1 cap, q2 cap and q3 cap. Now we may not require this q1 cap, q2 cap. These are vectors, while del square is nothing but this gives you a scalar quantity. Now del square is equal to 1 divided by h1, h2, h3 dou by dou q1 h2 h3 by h1 times dou by dou q1. Now plus, just continue as it is, dou by dou q2, and after 2 it comes h3 h1 by h2 times dou by dou q2 plus dou by dou q3 h1 h2 by h3 times the dou by dou q3. So this is what is del square in general coordinate system. Now if you write down it in Cartesian, we can write it as the h1, h2 and h3 for Cartesian are 1, 1 and 1. So we can write dou by dou q1 or dou by dou x of dou by dou x, which is mean nothing but dou square by dou x square plus dou square divided by dou y square plus dou square divided by dou z square. Now this is the del square in Cartesian coordinate system. You can represent it by x, y, z. Now for a cylindrical coordinate system, we have one row and 1 as the metric element. We can write it as here 1 row 1 as the metric element, and thus we can write it as 1 by row into dou by dou q1 is dou by, this is rho, phi and z, so dou by dou rho into, here you have h2, so it is rho dou by dou rho, okay, plus here you have dou by dou q2, which is dou by dou phi, h3, h1 and h2 in the denominator, so it becomes 1 by rho dou by dou phi, sorry, it's dou square by dou phi square, because here again you have dou by dou phi here, and 1 by rho you can take it out because here it is phi, with respect to phi rho is constant, so plus now you have h1, h2 and h3 here, so rho you can take it out, it becomes dou by dou square by dou z square. Okay, so so this is the del square in what I say, this is cylindrical coordinate system. So rho phi z. So del square in cylindrical coordinate system is in this way, and once again we can write it for spherical polar coordinate. Spherical polar coordinates, you have the metric element as 1 r and r sine theta, and the corresponding coordinates are r, theta, phi. Okay, so del square can be written as 1 by r square dou by dou r square dou by dou r plus, this is simplified form, plus 1 by r square sine theta dou by dou theta sine theta dou by dou theta plus 1 by r square sine square theta dou square by dou phi square. You can directly apply this general coordinate system formula in spherical polar coordinates also. Please try this and check you are getting the correct answer. So this is del square in r theta phi, that is spherical polar coordinates. Now let's move on to another concept of radial form of del. So that's radial form of the del. Okay, or you can write the gradient. How to get the gradient in radial form. Now if our function phi is or a curve phi is a function of only r, that means it depends only on the radius, then the gradient of phi of r, as you know, it gives a vector, is nothing but r cap dou by dou r of phi of r. Now, or you can also write it as the gradient of the function f of r, because it's just the function which depends on r. You can write it as r cap dou by dou r of f of r. Now this is usually used in central forces problem, central forces like gravitation, electrostatic force, etc. Now if our function f of r is equal to r to the power n, then del of f of r is equal to del r to the power n, which is nothing but r cap n into r to the power n minus 1. Okay, now a few examples we have. The first one is the del of r is equal to r cap, the gradient of the function r is simply r cap. Now del of r squared is nothing but 2 times the vector r into r cap, that's nothing but 2r vector. So r into r cap is nothing but the vector r, right? Now the third one, let us write down for r 1 by r, so it's nothing but minus r cap divided by r squared. Okay, now the fourth one, let us write down del of 1 by r squared. Now this is quite interesting. This we have, that's equal to r cap by 2 divided by r cube with a minus sign. Okay. Previous session we have seen the gradient, how to get the gradient of r square, 1 by r and 1 by r square. Now we are going to see the divergence in radial form. That means this can be used only when your function f of r is the function of only r. Okay. Now del dot f of r into r cap, this is the notation of gradient del dot f of r, that's given by 1 by r square dou by dou r of r square f of r. Right. Now the first one, let us see. If the f of r equal to r to the power n, then del of f of r is r to the power, sorry, it's not del, it's divergent of r to the power n r cap is equal to 1 by r square dou by dou r of r square f of r. Now f of r is r to the power n. Okay, r to the power n. So what is this? This is 1 by r square dou by dou r of r to the power n plus 2. So this becomes 1 by r square n plus 2 times r to the power n minus 1, sorry, n plus 1. Now this will be equal to n plus 2 into r to the power n plus 1 by r square is nothing but r to the power n minus 1. So divergent of r to the power n is nothing but n plus 2 r to the power n minus 1. Now similarly, let us see for other functions of r, like the divergent of r is equal to divergent of r into r cap is equal to 3. You just need to apply for this. Here n equal to r to the power 1, so n plus 2 is 3, r to the power n minus 1 is 0, so it is del dot r is 3. Now let us see for del dot r squared, so it will be equal to 2, so 2 plus 2, which is 4 r to the power 2 minus 1, which is r. So divergent of r square is 4r, that is del dot r square is 4r. Now del dot 1 by r is equal to 1 divided by r square. Here we have r cap, please don't forget that, because you need a vector here. And for n equal to 2 minus 2, for n equal to minus 2, when you apply it becomes 0. So for n equal to 0, del dot 1 divided by r square, we cannot use this particular formula. It is equal to 1 by r square r cap is equal to 4 pi delta cube of r. So this is the Dirac function. So del dot 1 by r square r cap is 4 pi delta cube of r. So this function can be used only when n not equal to 2. For all other cases you can use this. let us see now the curl of a vector in the radial form. Curl of a vector in the radial. Now del cross f of r into r cap, this value will be equal to 0 because radially outward it is moving. Now curl of a vector, it is nothing but an example is del cross a is equal to 0. Now del cross a equal to 0 means a is irrotational vector, which means it's curled, it doesn't curl. Okay, so this is equal to 0. Now for anything it is same. Now we can also have a concept on this, that is, if del cross f of r is equal to 0, then the f of r, function f of r, we can write it as some gradient of a scalar, gradient of some scalar. That means for every irrotational vector, or you can write it as conservative field, for irrotational conservative field F, there exists a scalar phi, such that gradient of the phi is equal to f. So this is the concept. If del cross f of r equal to 0, then you can write the function f of r as the gradient of some scalar phi. Now then this case it will be like del cross, so f of r we will writing it as gradient of the scalar. So the saying is curl of gradient is equal to 0. Okay, curl of gradient is 0. Similarly, we also say that the divergence of curl is 0. Okay, this is for any two vectors. This is the first one that we have written over here, and divergence of a curl means del dot del cross a. So this will be equal to 0 because this is the del cross a will be always perpendicular to this gradient. So this value will be equal to 0. Some formulas which are important in the case of del operator, that are the gradient of two function f g is equal to, let us name this as the first one, is equal to f times del g plus g times del f. Now del dot f times a is a vector because this is divergent. Del dot FA is equal to F times del dot A plus del F dot A. Now in this term, you must remember that you are going to get a scalar here, so each term separately must be a scalar. Okay, so del cross FA, so here you are going to get a vector because it is del cross, then it is F into del cross A plus del F cross A. Fourth one, divergent of A cross B. Now you are going to get a scalar here, so each term must be scalar. So B dot del cross A minus A dot del cross B. 5 del cross, so we are going to get a vector because it is del cross A, that's equal to del of, that means the gradient of divergent A, del dot A minus del square A. Sixth one is divergent of del cross A, so it's equal to 0, and seventh one we will write it here. This is another result which yields 0, so del cross del F, del cross del F is again 0, so del cross del F. Now this is 8th, del cross A cross B equal to A into del dot B. So your first term, here you are going to get the vector, so A into del dot B plus B dot del into A. So just reverse the order, B dot del into A. Now here you have minus B, so it continues. Okay, minus B into del dot A minus A dot del into B. So it becomes much easier for you. This is plus A into del dot B plus B dot del into A minus B into del dot A minus A dot del into B. Okay. Now this is a new concept here, the integrals. Now we are going to see what is line integral. The surface and volume. So line, surface and volume integral, this is what we are going to see. So let's write down what is dr as equal to dx I cap plus dy j cap plus dz k cap. So we can write the magnitude dr is equal to root of dx square plus dy square plus dz square. Now there are integrals, that is first one, the line integral, that is integral over the curve phi of r dr, and second type integral is integral a dot dr. This is phi of r is a scalar and here a is a vector. First one is parametric equation. What happens in parametric equation? That is, we can write x is equal to some function of t. Similarly, y is equal to some other function of t, and let us take another, z is equal to f, g and h of t. Okay, then we can write dx is equal to f dash of t dt, and dy is equal to g dash of t dt, and dz is equal to h dash of t dt. Now the integral phi of x, y, z into more the dr, that is magnitude of dr, is equal to, you can just write integral phi of t dt. You just have to convert all the x, y and z in terms of t for this particular integral. Or you can have vector a dot dr. This is the first one that we have seen in this case, and this is the second one, that is in the case of a vector a dot dr. That also you can write it as integral phi of t dt. Integral along a straight line joining x1, y1, z1 to another point x2, y2, z2. So this is integral, we are going to find out the integral value along a straight line joining two points. Okay, let's write down the 2 points, that is x1, y1 and z1 to point x2, y2 and z2. Now how to do that? We have to consider x1 minus x2, x minus x1 by x2 minus x1 equal to y minus y1 divided by y2 minus y1 equal to z minus z1 divided by z2 minus z1 equal to t. Okay. Now this is it. So the rest is as follows. The integral phi of r into dr is equal to integral phi of t dt, and integral a, this is from a to b, some point. This is A, this is B. Vector A dot dr is equal to integral phi of t dt. This is also from A to B. Now the next one, let us is along a curve y equal to f of x, integral along a curve y equal to f of x and dy by dx equal to f dash of x. Okay. So dy we can write it as f dash of x times dx, then integral a dot dr will be equal to integral phi of x dx. Now this is, so far we have seen about the line integral. Now comes the surface integral. Surface integral will contain two variables, and integral a dot ds. And what about this ds? ds in a Cartesian coordinate system, you can write it as dx dy along z cap, dy dz along x cap, and dz dx along y cap. So this is ds in Cartesian, and in cylindrical, so here this is for Cartesian coordinate system. Now cylindrical coordinate system, we have rho, phi and z. So it is rho, phi and z, and corresponding metric element 1 rho and 1, and d rho is equal to, what are the length element? D rho, rho d phi and dz. That means 1 times d rho, rho times d phi, 1 times dz. So it is ds, vector ds is equal to just multiply d rho, rho d phi. So it is rho d phi in the direction of z. Now this and this, rho d phi dz in the direction of rho, and now dz and d rho, d rho dz in the direction of phi. Okay, now that is the area vector in the case of a cylindrical coordinate system. And now we will see for spherical polar coordinate system. Now for that we need the coordinates r, theta, phi, and the corresponding metric element 1 r sin theta. So what are the length element? 1 times dr, so it is dr, r times d theta, so it is r d theta, and r sin theta times d phi, so r sin theta d phi. Now the ds, the area vector, is equal to dr or d theta. So r dr d theta in the direction of phi, then this one times this. So r square sine theta, r square sine theta d theta d phi, d theta d phi in the direction of r cap, and now this and this. So r sine theta dr d phi, r sine theta dr d phi, that will be in the direction of theta cap. So these are the area vectors in all three coordinate system. There will be 3 into 3, 9 area vectors. It's now Stokes theorem. It's to convert the from line to surface integral, line to surface, then integral a dot dr is equal to integral s into del cross a dot ds. Now here this is line integral a dot dr, we are converting it to surface integral del cross a dot ds. Okay, so this is Stokes theorem. Now here we have Gauss divergence theorem. This is from surface to volume. Integral, this is closed integral, a dot ds, that is the surface integral. This is equal to integral over the volume del dot a dot dv.